we'll continue with our second presentation, which will be made by John Strickland, a 30-year proponent of energy from space and a member of the board of the National Space Society. John.
Okay, this presentation was originally prepared for the Lunar Commerce Roundtable in Houston of last year, and I was able to go through the entire presentation in 15 minutes. So I'm going to try to move along fairly quickly to make up for some of the lost time that was lost to Bill Gates' products here. Let's see. Move this a little bit closer. There we go. First, there's some basic concepts of problems of loss of habitat. The biggest damage that is loss of species is due to loss of habitat, not pollution. The largest causes of habitat loss are population pressure and logging does not permanently occupy the land, whereas cities do. They occupy the land essentially permanently. Poor populations do not have the time or energy to think about conservation issues like pollution, global warming, when they're struggling to survive and feed themselves. So how do you reduce population growth, which is the thing that causes the permanent loss of habitat? It's called raising the standard of living. That's what's worked in the West. That's what works in most places. Population growth slows very rapidly when living standards improve. In Europe, there's several countries, especially in Northern Europe, would have a negative population growth without the heavy Islamic and other groups immigrating into them. And in fact, in some countries do have a negative population growth in spite of some immigration. So the first step to take care of this problem is getting cheap, abundant energy, which provides everyone with better living standards. The personal energy use, that's the rate per person, has increased about 10 times since the Middle Ages. Pre-fire humans were probably using about 100 watts, roughly about this per person all the time, which is about the same as a 100-watt light bulb. In some areas in Africa, very primitive areas, those rates are still somewhat similar, although most of them now are probably using about 3 kilowatts. The agricultural age, once you went to villages, this is basically outside of your own muscle power. That is the energy you gain from the environment around you. Probably using about half a kilowatt. During the Middle Ages, it was probably more than 1 kilowatt as they started to use various types of machinery and stuff. During the industrial age, it ramped up rather quickly by the middle of the last century, say in the U.S., to over 3 kilowatts. And we're currently somewhere in the range of 11 to 12 kilowatts continuous use per person in the United States and some other Western countries. This is sort of giving you a scale. Now, you can make a direct correlation, not necessarily cause and effect correlation, but nonetheless a valid scientific correlation between per capita energy use with birth rates, and of course birth rates is what causes population growth increase. So this is a logarithmic graph. Across the bottom, actually no, I guess this one isn't logarithmic, is the rate of, this is the arithmetic one, the rate of per capita energy use in kilowatts per person, and then along the left edge is the birth rates, 1,000 per capita. And as you can see, if you look at the upper part of the left edge, there's a whole bunch of dots. Most of those are in sub-Saharan Africa, where the per capita energy use is very, very low and the birth rate is very, very high. And if you plot this, I have another graph in another show. As a logarithmic graph, it shows up as a very nice straight bar. Spread out a little bit, but nonetheless a straight bar, which indicates that it's a valid correlation. At the extreme right end, there's a few countries like Saudi Arabia, Iceland, where you have very high rates of per capita use. Remember in this case that per capita use includes energy that is expended to supply you with products like heating, transportation, steel, wood, all the transportation that brings you your food to your local grocery store, all that's figured into the average per capita use. So we do need to reduce carbon use. In my estimation, the greenhouse effect is real. Unfortunately, because the greenhouse issue has been so heavily politicized, it's made it much more difficult to resolve the issue because one party doesn't want to admit what the other party is charging. So to be directly accurate as far as current information goes, I'm guessing that the actual greenhouse effect caused by people or natural causes is somewhere between 1/3 and 2/3, and that's that middle third that's really poorly defined. We just don't know where that number is until we get more accurate models and more accurate data from the Earth, and of course our satellite fleet is helping to gather that data now. The other question is on petroleum. We are using it up, but we're also burning it up. What would be is a very, very valuable chemical feedstock to produce chemicals, drugs, structural materials, whatever. It's very valuable and very unique, and we're burning it all up. When you look at coal, it's very abundant, but it does cause a lot of big problems. And of the other carbon fuels, natural gas has the fewest problems, but we're using so much of natural gas now that we're starting to run out of it in terms of supply. So how do we actually reduce our use of fossil fuel? Well, there's two ways you can do that. There's non-production solutions, such as making energy use more efficient, cutbacks of use, conservation, doing less with less. But if you only use these methods, you will eventually run out of energy. You must include production solutions also, and that's where many of the green groups don't seem to understand the business about running out of it, because there's a lot of reasons why energy use tends to increase all the time. And production solutions could include terrestrial alternate energy sources, nuclear fission or fusion, which isn't available yet, and space-based solar energy. But doing that is very hard because solar energy is intermittent and very expensive. Wind power is intermittent and remote. And both of those need to be stored if you're going to use it for baseload power. Baseload power is the minimum amount of energy that you need in your local energy grid all the time, 24 hours a day, say during the amount that you'd be using like at midnight or 3 a.m. Whereas your peak load is the difference between the base load and the highest amount of use, say at 4 or 5 o'clock in the afternoon. Nuclear power is scary both to people and politicians, primarily because of the news media use the nuclear power as a reason to make people watch their shows. It's a nuclear scaremonger club. Current launch costs are between $10 and $50 million a ton in terms of launching stuff into space. So right now, the solar power system is not economically feasible due to the incredibly high launch costs. Increases in general energy use tend to counteract attempts at reducing fossil energy use. So what are some of those reasons for the growth in energy use, even just in the U.S.? For example, new uses for energy, computers, server farms, shift to hybrid electric cars from gasoline, more use per person for existing uses, more users, population growth, which is caused by births in the U.S. population, immigration from other countries, and a longer lifespan and a lower death rate. So, do such high-capacity replacement energy sources exist on the Earth's surface? Many environmental groups say that wind power and ground solar are all that you need. They just do their arm-waving bit, and they never worry about the numbers. The basis of opposition to energy production by the Greens and the smallest beautiful crowd and all is they claim it's basically ideological, is Smell is beautiful. That's represented by the centralized power system. Now, a large building or a large power plant is bad because it's large. But how about a large mountain? A large mountain is inspiring. A large tree is inspiring. So just because something is large doesn't mean it's bad. How about the planet Earth? That's very large. How about the sun? That's even bigger. Is that bad simply because it's big? No. So this whole thing is an ideology. What's some of the other problems? Large companies, pollution, global warming, the location of a site caused by NIMBYs, the loss of habitat, and also one that's not as obvious, but one I've been tracking for many years, the fear of the destruction of nature by an energy-rich mankind. And there are a number of quotations that I have on that one. One of the guys says, giving mankind a source of clean, cheap, abundant energy would be like giving an idiot child a machine gun. And there are several other ones that I've collected that express the same idea from as long ago as the late 60s. So it's all ideological. So breakdown of the United States, no, this is breakdown of global energy use, I guess. 2005, I updated my values from 2000. In 2000, the total, which is about in the middle of the screen, was about 1,300. It's now grown to 14,500 gigawatts, which is, I think, 14 million megawatts, 14.5 million megawatts. So 1 gigawatt is 1,000 megawatts. So looking at the global, of that total, you have about 2,400 gigawatts of electricity. Like a medium-sized city uses 1 gigawatt of power, for example. Generating losses to produce that electricity accounts for about 2,600 gigawatts, which is wasted energy, but you have to waste the energy to produce the electricity. Fuel use is much larger. It's about 9,500 gigawatts. The world needs to replace about 10,000 gigawatts of energy to get rid of the carbon-based fuel, and the U.S. needs to replace about 2,300 gigawatts of energy to get rid of the carbon-based fuel. Now you'll see why that is true in the next image here. At the top of the graph, let's see, I should start with a heading here. This is the current global carbon fuel replacement chart for 2005 that I recalculated. And these numbers are based on the Energy Information Agency from the U.S. government. About 70%, or 10,000 gigawatts, has to be replaced to get rid of the carbon-based fuel, and about 31%, or 4,500 gigawatts, does not need to be replaced. So the gray box at the top there is your total global energy use. If you go to the right-hand side of the screen, you see that there's about 5,000 gigawatts of electrical use and generation of electricity. That breaks down to about 1,000 gigawatts of renewable electricity and 4,000 gigawatts of carbon-based electricity. You break down the 4,000 into 2,600 of generating losses. You don't need to replace those if you're going to use space solar power. You do need to replace the 1,400 gigawatts of carbon-based electrical use. On the left-hand side, in yellow, you've got your 9,500 gigawatts of non-electrical fuel use. That's 66% of the global total. That breaks down into the left red bordered box, 8,600 gigawatts of carbon fuels and about 900 gigawatts of renewable fuels. Now the 900 gigawatts of renewable and the 1,000 gigawatts of renewable electrical, the yellow and the blue box in the middle, both feed into that green box, which is a 1,900 gigawatts of renewable fuel and electricity that do not need to be replaced. And that, combining that with the 2,600 gigawatts of generating losses, it adds up to about the 10,000 that you don't need to replace. On the other hand, on the extreme right, the extreme left, excuse me, the 8,600 gigawatts of carbon fuels, which is 60% of the global total, combined with the 1,400 gigawatts of electrical use, adds up to 10,000 gigawatts. and that's the global total that needs to be replaced. And remember, that's like 10,000 cities across the country, medium-sized cities, similar to, say, half of Austin, Texas, as it is now, or about 1/4 or 1/5 of Houston. Okay, so here's your base and peak loads for a typical large city. The green is the base load, and the red is the peak load, and it fluctuates sort of on a sine wave on a daily basis. The time of the peak load that you get from the sun, it would be around noon, whereas the peak load for people is in the middle or late afternoon. Alternate energy sources are intermittent and cannot provide base load directly. The wind only blows part of the time, typically 20 to 40% in a good wind sites. And full sunlight, that sunlight that's directly overhead with no clouds, is not available at night, morning and evening, during cloudy or overcast weather, unless the sun is directly in line with fixed solar collectors, or if the very expensive tracking collectors are set up to track the sun, and that means you can only cover 1/4 of your ground collector site with collectors because the tracking collectors shade each other, and you have to space them quite a ways apart. And you also get very little energy during the winter months in most northern United States areas. I live in Austin, which most people would consider to be a fairly good solar site because it's in Texas. However, the insolation is the word you use for the amount of energy you get from the sun. In the winter, in insolation units, you only get about 60 in the Northwest and Great Lakes states, 160 units in southern Austin, about 260 units in parts of Arizona and California. This is amount related to the number of hours of sunlight, the number of hours of clouds during the day, and the height of the sun in the southern sky during the day. This is a map showing you roughly in December where the greatest and least amount of insolation is available. You can see it's pretty heavily concentrated in Arizona and Southern California, and with a moderate amount in Florida. In the wintertime, apparently we don't have the summertime slide. It's more evenly distributed. The wintertime is when you really have to worry about, because the winter is when you have the least amount of energy coming in, and that's what you have to base the size of your ground solar installation on. So there's a term I came up with called effective full sun. Effective full sun is the power produced when the sun is directly overhead at noon with no clouds. That's approximately equal to 1 kilowatt per square meter. If it's cloudy, you get much less energy, also the same during the morning and evening. So if you pack all the sun's energy for one day into a shorter period of full sunlight, that gives the EFS winter value for Austin, Texas in hours. That comes out to about 4 hours of full sun during the day, and in fact in some months the average is only about 3 EFS. That's if you squeeze all the available sunlight into just one shorter period of continuously full sunlight. Make it easy to compare. Now there's the graph showing the actual EFS values for Austin for 1 year, which ranging from a little bit below 4 in January up to about a little over 8 in the summer, and then down to just above 3 in December in the winter. And then during a given day, you also have to worry about your actual output during a day. Here's the power output for a ground solar plant sized to give you 1 gigawatt if the sun is directly overhead. Now that would be like for a base load or solar plants. This is during the summer and winter and cloudy days. The green is a base load plant like a coal or nuclear plant that you presume is running all the time, or you have a backup plant to provide power all the time. The red is the solar output you get from your 1 gigawatt solar plant during the daytime, and the sun being directly overhead is right at noon, the highest point. The winter values, you can see how it shrinks down a lot, and you also get less energy even during noon because the sun isn't as high in the sky, and during cloudy weather, you only get a small amount of total energy. So these are the realities that you have to deal with. Using tracking collectors, an Austin solar plant gets 4 EFS hours in the winter. A 1 gigawatt solar plant would produce 1 gigawatt hour for each hour of EFS per day. That's based on the size of the collector. So if Austin needed 1 gigawatt of power all the time, it needs 24 gigawatt hours of energy. That's 1 gigawatt for 24 hours. However, in winter, the 1 gigawatt solar collector plant would only produce 4 gigawatt hours on average. That's assuming you have 4 gigawatt hours every day. That's not including the times when you have 2 weeks of cloudy weather with no sunlight at all. That leaves on this optimal day with full sunlight 20 gigawatt hours to be supplied in some other way. So here's where you really get into the crunch. Baseload solar power means much bigger plants. You have to make your 1 gigawatt plant big enough to capture all the power you need in a 24-hour day in only just 4 hours of the winter sunshine. In addition, you have to generate the power that would be lost when you store the power and retrieve it from the storage. Using hydroelectric pump storage, which is one of the standard ways you store energy, very, very expensive to build, you need an 8.8 gigawatt collector generating 35 gigawatt hours in 4 hours of effective full sun. So here's the graph that shows that. The use of power from a 1 gigawatt solar plant intended to provide you with 1 gigawatt baseload power. The 8 gigawatt collector yields a total of 35.2 gigawatt hours using your 4 EFS hours of sunlight. 4 gigawatt hours are used directly as it's coming in from the sun. 31.2 gigawatt hours are stored. Of this amount, only 20 gigawatt hours return for use, so that's 4 plus 20 equals 24, and 11.2 gigawatt hours are lost during the storage and recovery process. This does actually deliver you 1 gigawatt for 24 hours, but your collector area has to be almost 9 times larger than a peak load, peak sun hours only plant. However, this 1 gigawatt system would be rather large. The collector would cover an area equal to that of a city like Austin, or roughly 350 square kilometers. It would weigh over 3.5 million tons. These numbers are based on an actual experimental solar system built in Austin about 10 years ago. We might reduce the area and mass of this maybe by about half now, because some of the efficiencies are getting up near 20% instead of 10%, but it's still huge. You would also need a massive pump generating facility and 2 reservoirs, which would probably cost about $12 billion, and that would not change no matter how efficient your collector is. You still need to store the energy, and there's really no other way of doing that. And this system, as described, has absolutely no reserve storage to cover 1 week of cloudy days. And sometimes in Austin in the spring or winter, we may get 2 weeks of cloudy days. Then what do you do? And this gives you an idea. This is one of the LUZ. Now this is actually a thermodynamic plant out in California. But a photovoltaic plant would look somewhat similar, and it would just be a huge array of things covering a very large area, stretching to the horizon. To give you some, I think that each of these LUZ plants produced 80 megawatts. That's less than 1/10 of the plant I'm describing. And actually the thermodynamic plants are slightly more efficient than the photovoltaic ones, but they require a lot more moving parts. So there's a drawback there. So the U.S. has an electrical base load, requires a base load of over 300 gigawatts. Base load solar power system to provide 300 gigawatts would require storage reservoirs totaling 1/3 of the area of Lake Erie. The collector site would cover an area of 90,000 kilometers square, or 30% the area of the state of Arizona. It would cost about $10 trillion and weigh about 1 billion tons. But wait, there's more. Remember the famous ads on TV where he says, but wait, there's more? we've only covered part of electrical use. The U.S. uses about 3,500 gigawatts of total energy. We haven't even included fuel use. So if we're really going to replace all that gasoline, you've got to generate hydrogen using electricity or do it some other way. And if the Greens want to do it all using solar power, you've got to generate about over 2,000 gigawatts of that with some non-carbon source. That's going to cost about $50 trillion, including the collector and storage system. The reservoir required, it takes 2 Lake Erie-sized reservoirs. Of course, it would be distributed over the entire U.S. to provide that much power. And you have to pump all the fuel from one reservoir into the other reservoir in 4 hours during the winter to get your power out of it. And again, there's no backup for a period of cloudy days. So this graph shows the area of Lake Erie on the left, the amount you need just to provide your electrical base load, the amount that you need to cover the total generating capacity, which is about twice your base load, and the amount required to cover all uses of energy in the United States in terms of the areas of the reservoirs that you need, not covering the areas of the solar collectors. I'm not even showing that. So the capacity of alternate energy systems is very limited because of the scale, the massive scale of the physical installation that needs to be acquired and the massive cost of these very large physical installations and the massive cost of maintaining them, getting rid of dust and rust and corrosion and all the moving parts. So that Kyoto Treaty assumes the existence of high-capacity, clean and affordable alternate energy sources to replace carbon fuel. The limited sites, limited capacity, and very high costs brings this into question. The limited sites, I showed you how limited they are in the United States in winter. The ones I'm talking about, you'd have to cluster them in Southern California and Arizona to make it work at all. If the capacity is not there, abiding by Kyoto means certain and massive cuts in our use of energy for home and work. The current Kyoto Protocol would cost the world about $40 trillion by 2050 and would be grossly ineffective, slowing warming by less than 1/5 of 1 degree by 2100. Attempts to use extremely uneconomical sources like ground solar to implement Kyoto now could consume the existing wealth and stop the creation of the new wealth needed for a system to completely fix the problem. Since human wealth increases every year and technological efficiency increases every year, the relative cost to fix the problem decreases every year. We cannot afford to fix the whole global warming problem now, but at some point we'll be able to fix the problem by using both old and new technology if we develop that technology. So how do you fix the problem? You should only try to use relatively economical energy sources, such as wind power if it's effectively sited, as a major carbon replacement source now. In other words, you don't want to go out and build energy sources that cost 10 times more than the ones you're using now, because it'll bankrupt everyone. We should develop new economical and clean energy sources with a very, very high capacity and thousands of gigawatts to provide the U.S. and other countries and avoid an energy war. And we need to develop very much better means of transmitting and more efficient ways of using the energy. And so I go here into the power satellite concept, which I'll go through very quickly because I think most people are familiar with it. Yeah. You just want to stop there? That's fine, because the rest of it is similar to what other people are going to present.
Thank you.
Do you want to have one question?
Yeah, please.
Any questions? Somebody in the back?
Yeah, John, I'm sorry. This is the first presentation I've been to. Has anyone discussed propulsion requirements for station keeping for keeping these things in orbit?
The thruster?
Yeah.
Yeah, well, I can discuss that later.
Okay.
Yeah, I think that can be dealt with. We better let the next presenter go ahead here.